Let's quickly recall what we did last time. Last time we introduced this abstract discrete structure called posets, partial order sets, which is an abstraction of an extension of this Boolean poset that we've seen. So last time we introduced posets and the very important duality theorem on posets. The duality theorem says, which is the Dewar theorem. Dewar theorem is saying that if you look at the maximum size of an anti-chain, then it equals to the minimum size of the chain decomposition. So for any chain decomposition we mentioned last time, it's always at least the size of any anti-chain. So the importance of Dewar theorem is that we have this duality phenomenon. The maximum of the upper parts it actually equals to the minimum of the lower parts. We proved it using induction on the number of points on the ground set P. Last time we have proof 1 that is induction on size of the ground sets P. So if you have a poset P, and here I will leave as exercise for you to prove. The second proof is proof using second one, which is exercise. Use symmetric chain decomposition. So the idea is use induction also to find symmetric chain decomposition. What does symmetric chain decomposition means? It's just a decomposition of the poset by chains, but every chain is symmetric. So here I need to tell you the definition of a symmetric chain. Roughly speaking, symmetric chain just means the starting point and the end points of the chain they are at the same position from same distance from above and from below. So formally, a chain in the Boolean lattice with inclusion relation, this Boolean posets is symmetric if it never, so this is, let me draw a picture. So here is a chain. Notice that we can take chain like these, which are very far apart in different layers, right? We can take a full everything and the empty set. This is a chain of size 2, but we skip many layers. So first of all, it doesn't skip any layer. Second of all, the starting point is some k and the end point is some n minus k. The distance, I might be off by 1 plus minus 1. You have to, let's call this chain, let's say this chain is called C equal to A1, A2. What's the best way to write it? Let's say this chain. Let me see. What I want to say is this is a symmetric chain, full length. This is layer 0 because the bottom is empty sets. Here is layer n, because it includes everything. So from level 1 to level n-1. Okay. So if we can write the elements as ak plus 1 to an minus k for some k from 0 to n, such that ai, each element in this chain is a set of size I at the ith layer. Okay, is the definition clear? So try to use induction to find the chain decomposition with the additional property that every chain is symmetric, and then using this to try to prove this duality phenomenon, try to prove Dilworth theorem. This is one exercise, the second proof. And there's yet a third proof from a graph theoretic approach. I will also leave it as exercise. So is the third proof of Dilworth. Basically, this is I can write it as a theorem. Dilworth theorem is equivalent to Koenig's theorem. So let me explain what is, or recall, if you have seen it before, what is Koenig's theorem. It's about vertex cover and matching in bipartite graphs. So consider, this is also a very important duality statement in graph theory. So consider just consider a general graph G, given a graph G. Maybe I'll give some definition first. What would be a good definition? Matching. So definition, given a graph G, we define the matching number. We all know what it is. It's just the maximum size of a matching, which is a set of edges that are pairwise disjoint with disjoint set of endpoints. So that I will not define it. Let's define vertex cover. So given the graph G, the vertex cover number vertex cover number of G. Let's also write tau of G, denoted by tau of G, is the minimum number of vertices to cover all edges. Here, what it means, cover all edges, means we have a set T such that T intercept the vertex set of every edge is now empty for every edge in G. Okay, so in other words, every edge has one of its endpoints in this set T. So if you think of a graph as a set system we've seen before, then this is basically the transversal number. It's the same as the transversal number of this graph G, right? So that's why I use tau of G. So in other words, this is again, remark, this is just the transversal number. Have I defined transversal number before? Let me just make this remark. This is a transversal number of G, same. Okay, let's observe a trivial inequality as we've seen in this comparing similar to the trivial inequality that any chain decomposition has to be at least the size of any anti-chain. This trivial inequality is for any G observation, for any graph, and for any the vertex cover number is at least the matching number. It's matching number. So tau of G is at least nu of G. Let's write matching number as nu. Why is this trivial? Well, let's consider, I will prove by picture. Consider maximum size matching. This provides us the matching number. We have nu of G many. What is the vertex cover? Vertex cover is we need to find a set of vertices such that every edge, one of its endpoints must be lying on this set of vertex cover. And since this matching are pairwise disjoint, we have to choose at least one endpoint from each matching. So this is, we have the above inequality. In general, the gap could be really, really large, but Koenig's theorem is saying if the graph is bipartite, equality holds. The gap could be arbitrarily large. So exercise, think of an example. So that their gap is large. Okay, this kind of simple example exercise, I really encourage you to do it, because one way of understanding and appreciating a statement is to through some concrete example to deepen your understanding. And you can associate some abstract results with concrete examples. This is another way to memorize it longer. So as I said, Koenig's theorem says for bipartite graphs, they are the same. For any bipartite graph G, the vertex cover number equals to the matching number. Any questions? So here's yet another exercise and another proof for Dilworth's theorem. Try to derive one from another. You can prove Koenig theorem using Dilworth's theorem, and you can also prove Dilworth's theorem using Koenig's theorem. So that's the proof, all the proofs. Maybe there's some other proofs of Dilworth's theorem. Now let's look at some applications of Dilworth's theorem. At the end of last lecture, we've mentioned that one way of applying Dilworth's theorem is it can be viewed as a very good quantitative Ramsey statement for highly structured objects. So recall Ramsey type statement. Ramsey theory, the philosophy. Did I spell it wrong? This is I forgot. So the philosophy of Ramsey theory is there exists within chaos, we can find there's always some order within chaos. So the concrete example we've seen is for any two edge coloring of a complete graph. So one such example is two-edge coloring of a complete graph. And this chaos is this two-edge coloring because we have no control on how the coloring looks like. Now, if n is large, we can always find order, and order is the monochromatic clique, a clique in which every edge is colored the same color. So the order is exist large. Here, large is actually, we know how large it is. We have a large monochromatic clique. Here, large is of order of magnitude log n. Okay. So as you can see, it's kind of like finding in any structure. In other words, this is any arbitrary structure. We can find homogeneous large. As long as the original structure is large enough, you can find large homogeneous substructure. So here, homogeneous means same color. In Dilworth theorem, homogeneous means in the posets, you can find them either pairwise comparable, so they form a chain, or they are pairwise incomparable. So for every pair, they have the same relation. This is what homogeneous means in Dilworth theorem. So let's recall. So Dilworth, the corollary of Dilworth theorem is for any posets, its height of the posets times the width of the posets is at least n. Let's say poset has n points. Yeah. So the proof we've seen last time, let me quickly remind you. Basically, by Dilworth, let me not squeeze it here. By Dilworth, we know there exists a chain decomposition C1 CWP. Exists a chain decomposition of size which equals to the largest anti-chain, that which is width of the anti-chain. So recall this is largest anti-chain. This is largest chain. Then their union covers everything. In particular, their union is of size exactly n. But each length is at most the height. So W times H is, yeah. So n equals to union of Ci, which is at most width of P times H of P. So easily we can derive that at least one of them is square root n. We can immediately get the improvement on this log n. Log n is tight for arbitrary graph. Here, again, as I said, you can construct the graph based on this poset P, where each point in P becomes a vertex in G. And you put an edge if they say comparable. This is so-called comparability graph. So this is saying comparability graph will contains a clique, which is a chain, or an independent set, which is an anti-chain, of size square root n, much, much larger than logarithmic. So this illustrates the phenomenon that when you have more structure, which is the transitivity property in posets, then you have stronger Ramsey statement. So in other words, we can define comparability graph, G for a poset P, where V of G is just points in P, and X is adjacent to Y in G, if and only if X and Y are comparable, i.e. X less than Y or Y less than X in the posets. So the corollary above says for any comparability graph, let's state it again as a separate statement. New corollary. For any comparability graph, so I forgot to say, so here, cliques is basically chain in P. And independent sets correspond to anti-chain. So any comparability graph on n vertices has an independent set or a clique of size at least square root n. And this is tight. So let's look at applications of dual theorem, in particular, applications of this stronger Ramsey statement to obtain some stronger Ramsey statement for geometrically defined objects. All right, again, what does Ramsey statement means? We start with some structure. In this case, we will see some geometric objects, a collection of geometric objects. And then we try to find homogeneous substructure, meaning that we find a subcollection in which pairwise the geometric subjects with respect to some binary relation, they behave the same. So this, as I said, remark, this illustrates dual theorem, illustrates that more structure implies better Ramsey. And so next, in this application, we will see a general phenomenon in many cases of in many geometrically defined structure, we often see much better Ramsey statement than this log n. We see much better Ramsey statements. We will see some today. And for some of them, the reason is that for this geometric structure, we can translate it, associate some poset to it. And because poset has better Ramsey statement, the original geometric structure has better statements. We will see some example. For which we associate posets structure. Hence, better Ramsey. So there's a question in the chat saying that for the matchings or tau of G, the vertex cover number, do we assume the graph is connected or not? We don't assume anything. The graph could be disconnected. It doesn't matter. Yeah, you just define it for all graphs. This conic theorem for any graph. And then conic theorem is for any bipartite graph. It doesn't have to be connected bipartite graph. Because assume you prove that for the connected one, then you apply to each component, you get. Okay, so what will be this thing? Let's start with the simplest possible geometrically defined graph. Let's look at real lines, one dimension real line, and look at intervals on the lines, all right? So let's consider example 1. Interval graphs. Let's consider a collection of intervals let's just assume we are looking at closed intervals, okay? It doesn't really matter. Oh, let me see. Yeah, let's just say it's closed intervals. So whenever we mention interval, we mean closed interval from A greater equal than A and less equal to B. Looks like this. So we have let's call this collection I. You have interval I1, I2, In. Let's say you have n intervals. Now, what can we study when we have a collection of intervals? We can study their intersection pattern as in extremal set theory, right? We are doing we are studying set system now. So here, the system of sets are system of intervals. So we cared about their intersection pattern. And for two interval, they could be disjoint, or they could be intersecting. All right. So we have disjoint, or intersecting. Then we can associate a graph to this collection of intervals. Think of every interval as a vertex. Then we can construct where this vertex set of the graph is just the n intervals in this collection, and 2 points adjacent if the corresponding intervals are intersecting. And you have I1 adjacent to I2 in G. You have two vertices adjacent if or only if the corresponding intervals are intersecting. All right. There is actually a graph, a name. This is called intersection graph. Of I. Meaning that if you have a collection of geometric objects, in this case, the geometric object is a collection of intervals, then you can define the intersection graph where each geometric object becomes a vertex, and two are adjacent if and only if the corresponding geometric objects intersect, right? And similarly, you can define disjointness graph, which is the complement of intersection graph. Two are adjacent if and only if they are disjoint. So similarly, disjointness graph is the complement of intersection graph. This is trivial. Now we can study the Ramsey statements in an interval graph. So what's the Ramsey statement? We start with the arbitrary interval graph on m vertices. We ask ourselves how large of a clique or independent set we can always find. That's the Ramsey statement. So first of all, let's translate what does clique and independent set means. So in this case, the clique means a collection of intervals, subcollection of intervals that are pairwise intersecting, right? Because for every pair, you have an edge in G in intersection graph. G pairwise intersecting. So it looks like this. You have these two intersecting, these two intersecting. This is a collection of pairwise intersecting intervals. All right, you have this real line. And what's the independent set in G? It corresponds to a collection of pairwise disjoint intervals. Very good. So it looks something like this. All right, I always draw some pictures if it's not clear. Well, first of all, let me leave as an exercise. I think it's a very cute exercise and very cute property of a collection of intervals on real line. That is, if we have a collection of intervals that are pairwise intersecting, for any pair, they intersect. Any pair, they intersect. Any pair, intersect. Then actually they have a common intersection point. In other words, there exists a point that appears through all intervals. They are commonly intersecting. Let's leave it as an exercise. This is a proposition, which is an exercise. Prove that. So any pairwise intersecting in any collection of pairwise intersecting intervals here I should use singular S or is or are. It seems like the object is singular, so maybe is. So any collection of pairwise intersecting intervals is commonly intersecting. So let me just make commonly intersecting. I say it's intersecting. In other words, i.e., so if this collection is I1 to IN, right? If IP intersect IQ is not empty for any PQ in N, then actually the intersection of all sets PQR is now empty. You can find the points that appear through everything. It's a cute example. Try to show it yourself. If you're familiar with Halley's theorem, this is saying the collection of intervals, they have Halley number 2. Anyway, good. Now we're going to prove a better Ramsey statement for disjointness graph. Let's first warm up to try to prove a weaker bound. So theorem. Oops. For any intersection interval graph, intersection graph of intervals, it has this special name, interval graph, let's say n vertices. For any n vertex interval graph G, there exists a clique or an independent set of size at least n to the 1/3. Okay, so once again, we should immediately realize that this is a much better Ramsey statement. For generic graph, we only have log n. Just remind yourself. So we have polynomial in n, which is much, much bigger than log n. So how do we prove this? As I said, for this graph, the idea is that we classify the edges in the interval graph by some partial orders. And then we repeatedly use Dilworth theorem. So the idea, which will be the same idea throughout several applications we will see today. Same idea here. Idea is to associate or classify, maybe classify is a better word. Classify edges of G by a bounded number of posets, partial order relations. And then apply Dilworth repeatedly, iteratively. Okay, let's illustrate this idea. So how do we classify the edges? Well, okay. In this particular case, we not exactly classify edges of G. We classify pairs of vertices of G, right? Classify pairs of vertices of G. Okay. Right. So maybe writing in this way is slightly misleading. So what I wrote here is correct, but I don't want to classify the edges of G. I classify pairs of vertices. So let me rewrite this statement, this weaker statement, in terms of intervals, not in terms of its intersection graph. It's the same thing, but I think writing in a different way is slightly better. Let me rewrite it. How do I rewrite it? For any collection of intervals, I1 to In, there exists a sub at least n over 3 of them that are either pairwise intersecting that are commonly intersecting or pairwise disjoints or disjoints. All right. Either intersecting or disjoints. Okay. commonly intersecting, yeah, here. All right, so how do we prove it? We're gonna classify, as I said, pairs of intervals by a bounding number of posets. In this case, we will use 2 posets. So what do? Proof. We define 2 posets. The first one is if we have interval that are disjoint, we define I less than I prime in the first posets if I lies on the left of I prime, very natural order, right? And this defines a partial order. You have transitivity. If I is disjoint from I prime to the left of it, and I prime is less than I double prime, then of course I is less than I double prime in this first order. So this is indeed, we have to check it's partial order. So you have to check transitivity. So we define this if they disjoint and max I is less than min I prime. Okay, obviously this is transitive, easy to check. This is transitive. So it defines a partial order, the first partial order. Now let's define another partial order. This is the first one. Second one is when we finish the disjoint ones. Let's look at the intersecting ones. But we don't define comparability for every pair of intersecting one. We only define those that are nested. So if we have 2, I and I prime intersecting, and then one is a subinterval of another, if I is a subset of I prime, all right? And it's also easy to check, this is transitive. If one is a subset of another, which is a subset of a third one, then of course the first one is a subset of the third one. Easy to check. This is again transitive. Okay, so the only thing that's not comparable in neither of the posets are what? These are not comparable, right? If we have 2 comparable, so if we have I prime, if I intersect I prime is not empty, and at the same time, how do I write it? I minus I prime is not empty, and I prime minus I is not empty, right? They have their own unique points. No one is contained in another. Then they are not comparable. Then not comparable in neither the first one nor the second one. Okay, now we can apply dual words. Okay, how do we do it? Before I write it down, let me just mention it. What do we know about dual words? It says that the height of the posets, the first posets, times the width of the posets is at least the total number of elements, n. What is height again? Height is chain. So a chain here is a collection of pairwise disjoint intervals, right? This means chain. And width is anti-chain. Anti-chain means they are not disjoint. Okay, they are not comparable in the first partial order. So either we have height times width. Either you have a chain of size n to the 1/3, then we are done. You have n to the 1/3 pairwise incomparable. Or you can find a subset of n to the 2/3 elements intervals in which they are pairwise incomparable. They form an anti-chain in the first order. Now you look at the second order, but on this set of n to the 2/3 elements. Apply Dilworth again. You know that either there's a chain, which means they are commonly intersecting of size n to the 1/3, which we have done, or there's an anti-chain of size n to the 1/3. Now this anti-chain of size n to the 1/3, it's an anti-chain in both I1 and I2, meaning that they must look like this, right? But use the proposition before. We know that they're pairwise intersecting means they have a common intersecting points. So they are also commonly intersecting. I think I made this proof too complicated. We can directly get n to the 1/2. Why? Anyone see it? Because we don't need to distinguish 2 and the rest, right? If they form a chain in the first partial order, they are pairwise disjoint already. So if they form an anti-chain in the first partial order, then that means what? They are pairwise intersecting by definition. And pairwise intersecting by this proposition means they are commonly intersecting. Then we are done. So I should have written it this way. So let me write it like this. And this is optimal bound, square root n, all right? Square root n such that they are either pairwise intersecting or pairwise disjoint. So I can delete these. I overcomplicate things. Okay. So define this partial order. So this defines a partial order P on I, right? Now by Dilworth, either a chain size square root n or anti-chain size square root n. In the first case, this is pairwise disjoint. We have square root n intervals pairwise disjoint. In second case, this is square root n intervals that are pairwise intersecting. Then by the proposition, we know that they are commonly intersecting. Let me just write intersecting. Okay. Any question? That's the first application to interval graphs. Now let's look at higher dimension. What are intervals in R1? They are convex sets in R1. Now let's look at higher dimension, convex sets in R2. So intervals are convex sets in R1. Let's consider those in the plane R2. So now instead of a collection of intervals, we have a collection of convex sets in the plane. And we want to say some statements like, if you have n convex sets in the plane, how large of a subcollection you can always find that are pairwise intersecting or or pairwise disjoint. In other words, if you look at the intersection graph of planar convex sets, how large of a clique or independent set you can find, right? So now the question is, given n convex sets in the plane R2, how many we can find how many of them we can find that are pairwise disjoint or intersecting. This, let's translate it. In other words, this is the same as for any intersection graph of n convex sets. How large an independent set or clique we can guarantee. How do you spell guarantee? Something strange. Guarantee. Okay. Here, as once again, the independent sets intersection graph are pairwise disjoint convex sets, and the clique, the pairwise intersecting here. I missed the pairwise words. Or pairwise intersecting. All right. Here's the question. This is a result of. So once again, we will see a polynomially large homogeneous set in this case. Again, different from generic logarithmic bound. This is a theorem by Larman, Matuszak, Hach, and Torresig. Okay, so what's the result? It says that we can always find n to the 1/5, n to the 0.2 of them, polynomial in n, many of them. They are pairwise disjoint or pairwise intersecting. For any intersection graph, n vertex, here we can always find at least n to the 1/5 many of them that are pairwise intersecting or pairwise disjoint. And what about the upper bound? Upper bound means we cannot find, there exists a intersection graph of n convex sets in which we don't have a really large independent set or clique number, right? So they prove an upper bound, and there are arrangements with no pairwise intersecting or pairwise disjoint planar convex sets of size n to the log 2 over log 5, which is roughly n to the 0.431. So improving this lower bound or this upper bound by some n to the epsilon, I think will be a very interesting result. This is a result in the 90s. So for over 30 years, there's no improvement. Even though both these bounds are quite simple, we will see this bound takes 5 minutes or 3 minutes for me to explain, just the same proof as we've seen above, using Dilworth theorem. Okay, we classify pairs of convex sets now by a bounding number of posets. In particular, we will use 4 of them. We use 1, we get square root n. You use 4 of them, you get n to the 1 over 5. You can kind of imagine, right? Repeatedly applying it. Then we get the results. So open, improving remark. Improving this will be interesting. I will not write this. So this is an open problem. So before proving it, I should make a remark which is worth making, is that we start with the interval graph, which is convex sets in 1 dimension. We witnesses a very strong Ramsey, which is square root n. Then, by this result of Larman, Matouchet, Puck, and Torosik, we see that in 2 dimension, intersection graph of convex sets also has very strong Ramsey statement, n to the 1/5 polynomial in n. Naturally, what should we think? 2 things. One is this bound best possible? We don't know. Improving it is open problem, I mentioned already. Second is, what about higher dimension? Very natural. In R3, R4, this remark I want to make is that in a sense, this is best possible. In R3 already, we are not expecting to have anything better than logarithmic. So here's a remark. We cannot hope for any super logarithmic little omega of log n bound for intersection graphs of convex sets in R3 already. This is because there's a known result saying that all graphs can be realized as intersection graphs of R3. So in particular, you just take those random graph that's really bad behaving in terms of Ramsey. They have logarithmic homogeneous sets, size sets, and you realize them as intersection graph of convex bodies in R3. So this is because it's known because by a result of Tiet, let me give you the reference. Well, okay, you can find a reference in this paper of this 4 author. Right? Airy graph, it can be realized as intersection graphs convex sets in R3. Good. So that end is a dead end. All right. I was about to move on, but there's a very good question in the chat, which illustrate that we should always ask questions, right? In 3 dimensions, it's a dead end to consider all convex sets. What about special convex sets? So Tier 1 in the chat asked a very nice question. What if we consider this cube? So that are basically boxes that are axis parallel. All its sides are parallel to axis, right? For example, 1-dimension interval, 2-dimension axis parallel rectangles, 3-dimension axis parallel boxes in high dimension. And we will see that for this special type of convex sets in high dimension, we do have a better Ramsey's result, almost close to square root n. So that's the next application we'll see. So let's first see this 2-dimension planar convex sets, the proof of these results. Okay. So as I said, the idea is given n planar sets in the plane, we're going to classify their pairwise relation by a bounded, in particular, 4 partial order sets, and then repeatedly use Dilworth. Proof. We should use 4 posets to classify pairs of planar convex sets. Okay, which are the 4? So the 4 would be okay. So did I give name? Let's give this name C. C is a collection of convex sets, and that's called, do I need? Okay, I don't need name. So C is a collection of convex sets. We only define when do we define it? Let me see. We only define comparability in all 4 posets if only if they are disjoint. In all 4 posets, two planar convex sets in C are comparable only if they are disjoint. Okay. So here's how we define it. The first one, you have 2 A, B. We say A and B is less than B in the first partial order if they are disjoint. And I need another definition. For any convex set C in C, we write pi C, the projection of this convex set to x-axis, right? The projection of C onto x-axis. So here's example. You have this set. Oh, it should be convex. This is not convex. So this is convex. This is my C in the collection. And you have x-axis, y-axis. And so the pi C would be, you project it down. this is ambiguous. Looks like almost vertical. Let's write it like this. Okay. So this is pi c. Okay. So in particular, pi c is an interval. Good. So two sets, disjoint sets, they are comparable in the first posets. If the projection of one is contained in the projection of another. So, and pi a is contained in pi b. So here's a picture. It looks something like this. You have a b like this, and you have a somewhere like that, right? So if you project it downwards to the x-axis, a will be a subset of b. Any question? The second relation, we say is the reverse. Oh, right. We need three conditions, sorry. The projection is contained in one, and also the smaller one is below the larger one. I forgot to say, okay? And A lies below B. And the second partial relation is the same, except that the third item is A lies above B. If you have A here, this is not convex, and you have B like this. If AB disjoint, pi A contained in pi B, and A lies above B. All right. So that's the second one. Then the third one, if the projection of one is contained in another, there's only these two possibilities. So now their projection is not contained, one contained in another. So the third partial relation is, we say A is less than B. Let me first draw the picture and then write down the precise definition. The picture looks like these. Or these. All right. So what's this definition? If the wait a second. Let me see. Let me write it down. If the third one, the left endpoint of pi b, so the minimum of pi b, left endpoint, is to the right, so to the left, no? The left endpoint of pi b. Let me see. The left endpoint of pi b is to the right of the left endpoint. Yes, that's right. So this is the left endpoint of pi b, which is here. And this is the left endpoint of pi a, which is here, the smallest one. And that's bigger to the right, right? Bigger than the minimal of pi a, which is this one. Okay. And the right endpoint of pi b is also to the right endpoint of pi a. Okay, meaning the max of pi b is also bigger than max of pi a. Max of pi b, which is the right endpoint, is to the, which color I haven't used? Purple. To the right endpoint of pi a, max a. So this is max a, max a. This is okay. And there's one more condition. This is one condition, and last condition. If pi a and pi b overlap, a is above b. Okay. The parts pi a and pi b overlap, a lies above b. So in this picture, all right? If they don't overlap, we don't care. If they have overlap, a is above. Okay. And the last one is exactly the same, except that the last part, a lies below. So either they completely to the one side, like this, they don't overlap, and you define this exactly the same. Or if they have overlap, a is down here. That's the only difference. So the last one, a is less than b in the fourth relation. If 1, 2, same as 3, but for 3, the overlap part, a lies above b, below b. So let me draw this picture. This is the same in both cases. So you have a, and in the overlap part, a lies below b. Okay. Good. There is some easy thing to check. I will leave it for you to check that if two planar convex sets, they are disjoint, then they must satisfy one of these four relations. Their intersection pattern must follow one of these four. That's the first thing. SI size 1 for any two disjoint convex sets in R2, they AB, they must satisfy one of these, meaning A is less than B for some I in these 4 posets. Second thing is that all 4 posets are indeed posets. They are transitive. Exercise 1, exercise 2. So it defines a poset. So let me just quickly explain one. Let's look at, for example, the first one, simplest one. Yeah. The disjoints and the projection contains another, and this lies below that. So if B is less than C in 1, that means what? The projection of B is containing projection of C, and B lies below C. So again, we have this natural order. One gets bigger, bigger, and bigger. So this is naturally transitive. All right, very easy. The others, you can check it yourself. So now we're almost done, right? Before I write down everything, let's just tell you the remaining of the proof by words, the same as we've seen in the interval graph. We first say, okay, let's look at the first poset. By Dilworth theorem, either there's 1/5 size n to the 1/5 size chain, which means pairwise disjoint posets. Pairwise disjoint planar sets nested in this way, right? We are done. Pairwise disjoint planar set of this size. Or you can find the anti-chain of size n to the 4/5. Now you forget about everything, just focus on this n to the 4/5 anti-chain with respect to the first poset. Look at the second poset on this n to the 4/5 elements. Either there's a chain of size n to the 1/5, which you get pairwise disjoints, you're done, or you have n to the 3/5 elements that form an anti-chain. You 3/5. Then you move on to the third one. You say, okay, on this n to the 3/5 elements, either you have a chain, and this chain, again, is also transitive. So you get pairwise disjoint thing, right? Pairwise disjoint of n to the 1/5, or you have n to the 2/5 anti-chain. Move on to the very last one. In the last one, you either have n to the 1/5 chain, you get what you want, pairwise disjoint planar sets, or n to the 1/5 anti-chain. Now, the final n to the 1/5 anti-chain is anti-chain in all 4 partial order. By this first exercise, that means this n to the 1/5 must be pairwise intersecting, right? If any pairs is disjoint, they must be comparable in some anti-chain, in some posets. So anti-chain in all 4 posets means they are pairwise intersecting. So this implies this first exercise implies anti-chain in all 4 posets are pairwise intersecting. Okay, so let's write down the remaining of the proof. Now, by Dilworth, apply Dilworth on P on the first poset. With the relation P, partial relation 1, we get either chain, which is pairwise disjoint, And we are done. Of size n to the 1/5 or anti-chain A1 of size n to the 4/5, right? Dual again. But now on the second poset, on A1 with respect to the second poset, right? On this set of n to the 4/5 elements, you get either a chain, which is pairwise disjoint of size n to the 1/5, or anti-chain A2 of size n to the 3/5, right? So in general, for I in 1, 2, 3, we apply Dilworth on AI with iteratively. When I equal to 1, you get this A2, right? With respect to the next partial order, right? We get either a chain of size n to the 1/5, which means pairwise disjoint, we are done, or anti-chain, the last one, A4, of size n to the 1/5. Oh, oops. N to the I plus 1 of size, what will be the number here for AI? Anyone? This number is one larger than this, right? So it should be AI plus 2. No, this is decreasing, right? This plus this is 5. This plus this is 5. So this plus this is 5. We have 5, 4 minus I. Okay? So when I equal to 4 at the end, I equal to 3, we get A4 of size n to the 1 over 5 anti-chain in all 4 posets. Which means pairwise intersecting, as we mentioned. Done. Any question? So let me mention this lower bound. So we can define this Ramsey function. Okay, I don't define it. So recall, this is the upper bound. The lower bound means what? There exists arrangement of n planar convex sets such that the largest homogeneous set is no bigger than this number. Okay? So we have a lower bound and an upper bound. So how do we construct this thing? We look at the intersection graph of planar convex sets. We will find the graph in which the largest clique or independent set is of this size. And this graph can be realized as planar intersection graph of planar convex sets. So for the lower bounds, for the upper bound, n to the log 2 over log 5 iterative blow up of C5 can be realized as intersection graph of planar convex sets. So what's iterative C5? Well, you start with the first step. You start with C5. Now replace each vertex by its own copy of C5. And between different vertices, you put complete bipartite graph. All right, so next step, it becomes this. Ah, I forgot I can just do copy paste, no? Very good. Huh? Okay. And you have all edges in between, all edges in between, all edges in between, all in between. So let's say this is, let's give it a name. How do I call it? C5-1, right? Then this is C5-2. Not a very good name, but you know what I mean. And the third step, this guy, it becomes its own copy of C5. For every one of these things, you do it again, you will get C5-3. Right? So let's look. For C5, let's say teeth blow up. Number of vertices is what? 5 to the t, no? Yeah, every time you multiply vertices by 5. What's the homogeneous number? Largest independent set or largest clique? Anyone? Look at the smallest one. Large independent set 2. Largest clique is also 2. Second one. How to be a clique here? First of all, you have to be clique in the original thing, right? To pick vertices. So if you want to be a clique, you have to pick vertices from adjacent block. And inside each block, you can only choose 2. So it's 2 to the 2. For independent set, it's the same. You choose an independent set here, you have to choose a non-adjacent block and choose 2 here. So it's 2 to the 2. In general, 2 to the t. 2 to the t. So if this is n, this is n to the log 2 over log 5. That's it. So can you come up with a better construction that can be realized as intersection graph of planar convex sets? I will not mention how to realize these. This is a little bit geometry. It's not very difficult, but not immediate. Not immediately. You can, if you're interested, you can look up their paper. Okay, we focus just on the extremal problems. So I will omit this part. Any question? So as you can see, let me mention one more time, this n to the 1/5 proof is really short. You just find 4 posets characterizing them and apply Dilworth repeatedly. But somehow for 30 years, we cannot improve it, okay? Next time, so today time's up. Next time, next Tuesday, we're gonna mention one more application of Dilworth, which is this one asked by J1 in the chat. Even though for convex bodies in 3-dimensional above, we don't have any good Ramsey bound because all graphs can be those graphs. But for special shapes, like axis parallel boxes, we can get really strong bounds, Ramsey type bound, okay? Any question?